All right, so we start with generating functions. Actually, there are other ways to solve counting problems. The simpler ones, you could use combinations, permutations, and those kind of things, right? And the usual sum and product rules for counting. But as we saw on Monday, for a lot of problems, it's very complicated to use those tools. And instead, we model the counting problems as a recurrence relation. So for example, here's an example here. We want to find the number of bit strings of length n that contains 2 consecutive zeros, then we model it as a sequence, yeah, as a sequence where in the sequence an represents the number of bit strings of length n that contains 2 consecutive zeros. So for example, A0 and A1 is 0, both are 0 because there is no bit string of length 0 or length 1 with 2 consecutive zeros, right? Meanwhile, there is only one bit string of length 2 containing 2 consecutive zeros, and there are 3 of bit strings of length 3 that contains 2 consecutive zeros, namely 001, sorry, no, yes, 001, 000, and then 0, then 100, right? Yeah. Okay. So now, then the idea is then look at this as a sequence, so A0 up to AN and so on. And then the aim is to solve this sequence. Now we showed that this could be, or we could show that this could be represented as this recurrence relation. Now then the question is, how do we solve this recurrence relation? How do we get the closed form of the recurrence relation, or the explicit form of that recurrence relation? So you want to say, what is AN? Yeah, in terms of n. So only, not in terms of the previous terms in the sequence. Now, so the idea then is to use a few methods. So one of them is generating functions. So generating functions are structure that can be used to represent a sequence. So it is not by itself. The aim is not to use it for computing values, but rather to represent a sequence. For example, if we have the sequence 0, 0, 1, 3, 8, 19, 33, 84, and so on, yeah, then the sequence could be represented by an infinite summation or infinite polynomial expression called this, or look like this. So 0 times x to the power of 0, 0 times x to the power of 1, and so on. So 1 times x squared plus 3 times x cubed plus 8 times x to the power of 4, and so on, right? Which is, of course, this one. So look at this form as a representation of this sequence, not as something that you calculate, right? So it's not something that you put a value of x and you get something. No, it's a representation of that sequence. So this is the x to the power of 0. This is the coefficient of x to the power of 1, x squared, but x cubed, and so on. Now, then the idea is then to manipulate that generating function so that we can find a solution to counting problems. So that's the idea, right? So we will see that today and next Monday. So for now, however, we will work on only on the generating function. So we're not we are not trying to solve the counting problems yet. So we look at the generating functions first. So generating function of the sequence A0, A1, A2, and so on is an infinite series of the form like this. Yeah, so it's infinite, right? So infinitely long. Yeah, A0 plus A1. Of course, if the sequence is finite, then you could write it in a finite way, infinite form, but generally it's infinite. Now this form is also called a formal power series or power series. Yeah. This is with z. Yeah. Okay. So the value of z here is not intended for calculation. So you usually do not put z, the value of z. Don't put z something, right? So ignore the value of z. Consider z as simply a symbol. All right. Now, then of course, in some cases, some operation require that the series converge. So in that case, z may be assumed to be close to 0, but we never say what's the value of z, and we do not compute gz by putting z inside, by putting the value of z inside. All right. Yeah. At most, what we can do is we assume z to be close to 0, so less than 1 and very close to 0. All right. Now, so how do we use that, right? So first, let's consider this infinite sequence. What is the generating function of this sequence? Can you guess? Can anybody guess? Look at this. If the sequence is A0, A1, A2, and so on, then the generating function is A0 plus A1Z plus A2Z squared, and so on, right? So that means the generating function of this sequence is this. Yeah, I use X in this case, but it doesn't matter, X or Z, right? Yeah, which is, of course, if we make it slightly more compact using some notation, the summation notation, then you could get something like this, right? So the 3 here, so all the coefficients are 3. So therefore, we write it down like this, right? Any question?
No, sir.
So no, okay, good. So it's clear, right? So what's the next one? What is the generating function? Can anybody guess?
1 plus 2x plus 3x squared plus 4x cubed.
All right, good. And if you write it as summation, the sum of
k from 0 to infinity, where k plus 1 times x to the power of k.
correct, yes. Yeah. All right, good. What about this one?
It's 1 plus 2x plus 4x squared and 8x cubed.
Yes. And so on, right? And if we write as a sum, what is the sum form? The summation form? We use summation notation. What is it? Sum from k to from 0 to infinity of?
Is it k times 2, sir?
Sorry,
Is it k times 2?
is it really k times 2? This is k0, this is k1, this is k2, this is k3. What will be the what will be the next term? Should be 16x to the power of 4, right? This is k4. So what is the sum? sum of k from 0 to
power of k.
correct, to the power of k, x to the power of k. Yeah. All right. What about this one? Now this one is finite. Yeah. Then if this one is finite, then it's you simply spell it out, right? So like this. So 1 plus x squared plus x cubed plus x squared 4 plus x squared 5. Yeah, there are 6 terms, so we have from k 0 to 5. So this gives us this. Or you could also, yeah, well, this is exactly what we want, right? Yeah. Good. So it doesn't have to be infinite, so it could be finite as well. What about this one? This one is so 0 0 1 1 0 0 2 2 0 0 3 3, and then what you could guess, of course, next is 0 0 4 4, and then 0 0 5 5, and so on, right? Now the generating function is x squared plus x cubed plus 2x power 2 times x to the power of 6 plus 2 times x to the power of 7. Remember, this is 0 1 2 3, yeah, and then 4 5, this is 6 and 7, and then this is 8 and 9, this is 10 and 11, and so on, plus 3 times x to the power of 10 plus 3 times x to the power of 11, and so on, right? So you have two every 2 terms you have 2 terms with coefficients increasing, right? Now if we write this as a sum, what you get is slightly complicated, namely like this. So what we do is, well, we take out, we could simply consider this like this separately, yeah, as one term, and then take these out, yeah, so you get x squared plus x, well, x cubed. And what about this one? This is times 1 times 2x to the power of 4 times 3x to the power of 8, and so on, right? So this gives us this. Yeah, it is also possible to be this way. All right. Any question? No? No, if not, then let's continue. So if you look at this form, this is not yet a closed form. So what I mean by that? So for example, some generating functions could be written without expressing it explicitly as a summation. So for example, like a finite or infinite summation, for example, I have this finite sequence 1 1 1 1, so 6 terms, all are ones, and the so what is the sum form? Can anybody give me? Well, we already have it, right? It's the sum of k from 0 to what?
X to the power of k. Until yeah,
until
5.
correct, until 5. Yes, exactly that, right? So that is exactly, or let me use z. Yeah. Now then, what about this one? Can we simplify that so that we get something, so that we get rid of the summation notation? We get rid of the summation notation. It turns out we could do that. We have this. Yeah. So instead of summation like this, we could write it like this. So without summation. Now, this form and this form is called the power series form, of the same sequence. Yeah, power series form of that sequence, and this form is called the closed form of the generating function of the sequence. So this is the power series form of the generating function, and this is the closed form of the generating function. So maybe your question is, how do we get this, right? So we will see some of the techniques later, right? Let's see. All right. Now, the key thing here is that when you use generating functions, we may need to convert between these two forms. So that means, when we work with them, sometimes we want to convert from the power series form into a closed form and the other way around. So, therefore we need to know how to do it, right? So let's have a look. So let's take a look at few examples. One in which the closed form is rather simple. So for example, this sequence, what is the generating functions of this in terms of the power series form? Then the first one would be, well, actually, this is equal to 1 is actually combination of 0 from 2. 2 is combination of 1 from 2, and 1 is combination of 2 from 2. All right. Now, what is the generating function? Can you write? This is 1 plus what?
2z
2z, and then
plus
plus?
z squared.
Correct, z squared. Yeah. Now, okay. Now, then, what about the second one? Should be rather straightforward. Should be dz is 1 plus 3z plus 3z squared plus z cubed, right? And so on. So, for example, this one, yeah, this one. What if I wanna? What would be the if I wanna? This is where the base is 2, 3, and 4. What about 5? What do you think is the sequence? 1. So if this is of the form n combination k from n, and this one is n is 2, and this is n is 3, n is 4. What about n? If n is 5, what do you get? The sequence is what?
1 5 10
Mm-hmm.
10
Mm-hmm.
5 1.
Correct. And which gives us, of course, this is the sequence. This particular sequence, yeah. Which is, of course, the generating function is 1 plus 5z plus 10z squared plus 10 z times z cubed plus 5z 4 plus 1 also of z 5. Yeah. Now then, of course, the question is, what is the closed form of such sequences? All right. So, fortunately, we can use some theorem from algebra. This is an algebra. In algebra, we know that this form, x plus y to the power of n, is actually this. That is, for example, you have x plus y is, of course, x plus y, right? But the coefficient is actually 1 times x and 1 times y, which is, of course, 1 x of 1 times y of 0 plus 1 x power. So let me start with 0 here. 0, 1, yeah, 1, 0, right? Yeah. Now, of course, it's the other way around is fine, right? So all is just the same, of course. 1 0 x or 1 0 and 1 x or 0 1 1. Now what about x plus y power of 4, for example? Then this is actually it's quick. You could do it very quickly. So it's actually x plus, sorry, x power of 4 plus x power plus 4 x cubed y plus 6x squared y squared plus 4xy cubed plus y over 4. Yeah, which is of course 40 x power of 4y 0 plus 4 you take 1 from 4 x power of 3 y power of 1 plus you take 2 from 4 x squared y squared plus this and this. Yeah. Now, of course, you know that nk is equal to n minus k, all right? So therefore, this is the same as for 4 y for 0 plus 1 x. So for 3 x power of 3 y power 1 plus taking 2 from 4 and finally taking 3 and then taking 4, taking 0 here, so should be 1 0 and then this is x for 0 y or 4. Yeah, so which is of course this. Yeah, now if you're not sure, try multiplying this. Yeah, you will get this form. Yeah. Now with this theorem we could get this. So if the generating function, if the sequence is this, then the generating function is this, or in the closed form it will be this. Yeah, right. Okay. Yeah, any question at this point? No question?
No, sir.
No, so it's clear, right? So that means if I have this series, yeah, then the generating function is, of course, sum of k from 0 to 1 to 0, 0 to 5, yeah, 5 k z power of k. Yeah, which is of course 1 plus 5z plus 10z squared plus 10z cubed plus 5z for 4 plus z for 5. Now, and as we saw in this theorem, this is actually the closed form will be 1 plus z. Yeah. Okay. Now, so these are the finite sequences which are rather interesting. Now, remember that we do not use generating function to calculate the sum of the series. We do not use that to calculate, but rather we use it only for expressing the finite or for infinite sequence, right? So So then what's the point of having this representation? The idea is that if we have this sequence, then we could represent this sequence using this form. Now, then later on, we could combine the two different sequences by, for example, adding them, multiplying them together, and so on. So that's our main idea here. Now, let's have a look at the infinite sequence first, right? So what about this infinite sequence? Now, in this infinite sequence, consider the sequence of an is equal to 2 times n plus 1. So that is the sequence 2, 4, 6, 8, 10, 12, and so on. Yeah. Then the resulting function is, of course, 2 plus 4z plus 6z squared plus and so on. You see that? And this is the summation, the sum form. And we will see how this would be represented in closed form. So let's see a few other infinite sequences like this and this. Yeah. So if all four, then you have this, and you have like this. Yeah, 5, 6, 7, 8. Then the generating function is this one. So what will be their closed form, right? Now we have to start somewhere. So let's start from the simplest case, one of the simplest case. Now, borrowing a little bit from calculus, you know that the limit of this sum, given that t is close to 0, yeah. So for example, t is close to 0, yeah. Yeah. The limit of this sum for when n goes to infinity is actually this. So let me ask, is this correct? How do we know that this is correct? Can anybody know? Can anybody tell me how do we get this formula? How do we get this? You guys remember the series, the summation series? Yeah. Matthew?
Is it from the geometric summation series?
Correct. Very good. Yes, it is geometric series actually. Yes. So if you have a geometric series like this, right? 1 plus 2 plus 4 plus 8 plus 16, for example, this is actually 1 times, what is it? 2 to the power of n. What is the n? 5 minus 1 plus 1. Sorry, what was the what was the formula? Why did I forget about this? Should be so that would be 8 times n. Is it this one? Right? So that means 1 times 2 to the power of 5 minus 1 divided by 2 minus 1, right? Which is, of course, in this case, 12 minus 1. Yeah, which is 32. Now, all similarly, if we have this, plus 3, plus 9, plus 27, plus 81, plus 343, plus 79, for example, this would be 1 times 3 to the power of 1, 2, 3, 4, 5, 6, 7 minus 1 divided by 3 minus 1. Yeah, which is, of course, 1/2 times. Yeah, which is, of course, then you would have it, right? Now, what if the ratio is less than 1? So for example, 1 plus half plus this plus this. As there will be 1 times 1 minus a half divided by 1 minus a half, right? Which gives us, oh, sorry, 1 minus half power of 5, right? Yeah. Right. So now this gives us, of course, 1 minus 1.5 power of 5 divided by half, right? Now, what if we have something like this? Goes to infinity. Then essentially, yeah. Then this gives us that this is actually 1 times 1 minus a half power of n divided by 1 minus 1/2, where n, this is limit n goes to infinity, right? Now what happened is that this is actually, when you have that limit, this is actually 1. This means it goes to 0 because n goes to infinity. Yeah, this term goes to 0, so that means we have 1.5. Yeah, 1 times 1. Yeah, 1 times 1 over 1 and minus 1/2, which gives us, of course, 2. Yeah. So in fact, this is what happens, right? If the ratio is t, then it's 1 over 1 minus t. Now that's what we want. That's what we use. So therefore, our theorem says that if we have this generating function, all ones, infinitely many, the generating function is this. Yeah, clear. And it is equal to this. So you see, if we have this infinite sequence, can be represented by this simple expression. All right. Remember, we do not calculate the value of that function based on value of z. So we don't care. We don't even care what is z here. We just use z as a symbol here. Why do we get this? Well, because the ratio between these two terms is z actually. Yeah. All right. Good. Yeah. So, any question at this point? No. Oh. Now let's have, so I have a few results, but rather than going through this result, let's just look at examples. Yeah. Directly, all right. So I think this will be easier, right? Let's start with this one. The generating function is, let's call it GZ, is what? What do you think? What do you guess? Can you guess? What is GZ? This is very easy.
1.
Correct. Yes. Thank you, Matthew. And that's it, right? We don't need to. This is already in a closed form. What about this one? This is okay.
Z cube.
Z cube. All right. So how do we get Z cube then? Well, GZ is 0 times Z to the power of 0 plus 0 times Z to the power of 1 plus 0 times Z squared plus 1 times Z cube plus 0 times Z to the power of 4 plus 0 times Z to the power of 5 and so on. So that means we only have this term, right? So that is Z cube. So this is already a closed form. All right. So what about this one? Now, what about this one? Now, C is a constant. What is the generating function? This is what? Let's write it down first, right? What is the power series form? What is the sum form? So it's 1 plus, anybody? So for example, if C is 2, then you have like 1, 2, 4, 8, 16, and so on. So what about generally for C? So what do we have here?
1 plus CZ
CZ and then
plus
plus,
C squared Z squared
correct?
plus C cubed Z cubed.
Oh, sorry, with the plus. Yeah, Z cube plus and so on, right? Which is what? Sum from K from 0 to infinity.
C to the power of K, Z to the power of K.
Correct. No, good. So what is the closed form? We use the same idea as what we've seen for the sequence 1, 1, 1. We know that, right? So how do we get this? We get it by geometric series, right? So for the closed form of this, observe this, yeah, or observe this. There is a constant ratio between two successive terms. So therefore, so for example, we know that this gives us the ratio. So this is geometric series with ratio between terms given by C, right? So because, for example, A1 over A0 is C, which is also A2 over A1, A3 over A2, and so on. They are the same, right? It's all C. So therefore, the closed form is, of course, GZ is 1 over. So not C, CZ, sorry, CZ. C times Z. So that means 1 over 1 minus, can anyone guess?
CZ.
Correct, 1 minus CZ. Now we use that, right? So we use that. So that is, if we have this geometric series, we could do this, yeah? Now we use this formula for this one. GZ is 1 minus Z plus Z square minus Z cube plus Z to the 4 minus Z to the 5 and so on. And this is 1 over, this is geometric, right? With ratio, right? What's the ratio between the two terms?
Minus Z.
Correct, minus Z. So therefore, this becomes 1 over
1 plus Z.
1 plus Z. Correct. Now, what about this one? GZ is 1 plus what else? 1 plus what?
Plus Z squared.
Plus Z square plus
Z to the power of 4.
Z to the power of 4 plus Z to the power of 6. So this gives us is 1 over 1 over what?
Z squared.
Z square.
1 minus Z squared.
Correct. Yes. Yes, correct. Good. Now what about this one? Oh, by the way, I forgot. This is, if you write this as a summation, this looks like this, right? K infinity minus 1 to the power of k z to the power of k. Yeah. Okay. Now, what about this one? This is write as a sum. This is sum from k from 0 to infinity. So it's 2, not 2k. But what was it? Hold on a second. There should be a way to write it down simply. Let's go back to that later. Yeah. Well, let's just use this example first. Yeah. So gz is 1 plus 3z square plus 9z cube plus 7. So plus 3z. Forgot about this one. 9z square z cube plus 81z, 4 and so on. Now this is, of course, if you look at the ratio is 3z, so it's 1 over 1 minus 3z, right? Yeah. Okay. So that's some illustrations, right? So where we could use the idea for geometric series. Yeah. And this is in fact sum of from k to infinity what was it? The 3 times k z times k. Now this one is sum from k from 0 to infinity with the ratio z square, so it's actually z to the power of 2k. Right? Yeah. Any question? No? If not, then let's move on to the next one. What about this one? Any idea? Any idea how? Let's have a look, right? So 1, 2, 3, 4, 5, and so on. That will, the generative function is this. Okay. So what is the generative function of that? How do we get the solution? Well, let's have generating function of this. Let's call it fz. Yeah. So is gf for this. As we saw, fz is actually what? This one, right? This one over 1 minus z, right? Now, what is the relationship between f and z here? F and g, sorry, with f and g. Can you get g from f? Can you guess what kind of polynomial is g? Hello? Can you guess from calculus? Is there anything rings to mind? Do you remember anything from calculus? No? What is the relationship between z square and 2z? Also z cube and 3z square. Z to the power of 4 and 4z to cube.
The
What is the relation?
derivative.
The derivative, yes, exactly. That's the derivative. So that is essentially, you see here, turns out that gz is the derivative of, sorry, of f, right? So, yeah, so gz is derivative of fz. Now, so therefore, the derivative of fz, a derivative of this, is what? This is what? Can you guess? This is the derivative of this, right? 1 minus z power of minus 1, correct? So which is minus 2 so minus 1 times 1 minus z times 1 over 1 minus z. Hold on a second. What was it? So this is right. This times minus 1, correct? Yeah, which is of course 1 over 1 minus z squared. Yeah. Any question? No?
No, sir.
Yeah. So essentially, actually, this sequence would have this generating function as a closed form. All right. So we will see more examples on Monday, and then also a few examples on how we use this with the counting problems. And then after that we will discuss several solutions to several worksheet or quiz from week 4 up to week 6. I think we will pick some of the solutions and we will discuss that. All right. Any questions so far? No? No questions? If not, then let's conclude the sessions today and stop the recording.